Hello, everyone. Welcome to the Parsons Technical Webinar Series. I'll be your host today, Jessica Bennett. Today we have with us Louis Manzella and Jim Schutz presenting on uncertainty analyses, contaminant fate and transport modeling from fundamentals to applications. We'll go over a few housekeeping items first. We'll be keeping all phone lines muted until the Q&A session at the end. If you have a question during the webinar, feel free to submit it at any time in the chat feature, or you can hold it until the end if you want to ask it live. This webinar has been approved for 1 professional development hour or PDH credit. If you'd like to receive a PDH certificate for today's webinar, there will be a link posted throughout the webinar a few times that will have a few multiple choice questions on it that you'll need to answer for credit. I will also post those questions in the chat in case you have any issues accessing the form during the webinar. And if you have any issues downloading that form, you can request it from us by sending an email to daniela7@parsons.com. And finally, this webinar is being recorded and will be available on the Parsons YouTube channel in the next few days. So a brief agenda for today, we'll introduce the guest speakers, followed by a core value moment, and then the technical presentation, and then we'll wrap up with questions and answers at the end. So a little bit about our 2 speakers. Louis is a geologist with Parsons with experience in groundwater and surface water modeling, including alternative modeling suites and open source methods for data collection and processing. He has a unique set of experience with a wide variety of data collection technologies, including Internet of Things, long-range radio communications, and telemetry. Louis earned his bachelor's and master's from the University of Buffalo. Jim Schutz is a principal hydrogeologist and technical director of environmental geological services here at Parsons. He has 24 years of experience specializing in groundwater modeling, investigation, and remediation of sites in complicated geological environments. He also earned his bachelor's and master's from the University of Buffalo, and he's a professional geologist in New York and Pennsylvania. And with that, I'll hand it off to Jim for the core value moment.
Thank you for that, and thanks for the introduction. I appreciate everyone taking time out of their day to listen into this very exciting topic of uncertainty analyses and groundwater modeling. To get started, at Parsons, we have the 6 core values that are shown here, and today we're going to share a safety moment, and that safety moment is emergency preparedness. Hopefully, you've all thought about and have enacted a plan. Make sure that you have a plan for emergencies. Hopefully, you've all built an emergency kit, first aid, stay informed. These are all the tenets of a good emergency preparedness plan. What I would like to add to this on the bottom is to make sure that you inspect, maintain, and update the plan, the kit, your first aid training over time, so that if unfortunately you have to evacuate your house or stay in your house for some amount of days, everything that you have already prepared is still intact and in good shape and ready to go. So for a general outline of this presentation today, there's 3 main topics. The first topic is uncertainty fundamentals. From there, we'll discuss tools for quantifying uncertainty. And lastly, we'll close out the presentation with a look at a specific toolkit that we've developed here at Parsons for analyzing uncertainty as related to PFAS compounds. So for uncertainty on fundamentals, as we start to talk about this topic, I pulled in this quote from Alan Greenspan: "It's better to be roughly right than precisely wrong." So here's a little demonstration of uncertainty, as it's called, the circle of uncertainty. And this may be something that you were shown in high school or in college in terms of mathematics, statistics, and or uncertainty. So what this demonstration here is if we look at the circles on the left, we have a black circle. So that's the actual circle that you're trying to draw in this hypothetical example. And then you have an upper limit of accuracy of your device. Let's say you have a compass and you're going to draw this circle, but your compass in this case is not very good at drawing circles. And you have a very high upper limit of accuracy and a much lower limit of accuracy. We've sort of exaggerated that just for this presentation. But what you can see here is on the right, when you go to start to draw a circle, and again, this circle's fairly poor, this compass is fairly poor at drawing circles, but if you draw multiple circles, and the analogy here is each one of these colors is another model run. Over time, as you draw more and more circles, you start to develop a suite or an ensemble or a set of model results. And with that set of model results, you can get a better idea of what the true radius of the circle is and understand it through some sort of central tendency. If you think about, the plot that we've all seen where we talk about accuracy versus precision and, as related to a bullseye, this example here with these many circles is essentially a highly accurate estimate, but of low precision. When you do have this set of model runs, essentially, then what we can do is uncertainty analysis and quantify uncertainty. So what is uncertainty? First of all, uncertainty is not error. Error is really the difference between the true value and the modeled value. This may be related to how you're measuring things. This may be related to how your calculations are being done. But it's important to remind ourselves that uncertainty is not error. Uncertainty is a possible value for a given measurement or estimate. Uncertainty analyses. Most of the premise of this presentation today is related to uncertainty analyses, and those are ways of quantitatively evaluating uncertainty in model components. So what is the uncertainty behind the input variables, the parameters, the equations, and in some cases, the calibration itself? And uncertainty is also an examination of the procedure and all possible sources of error, not just a quantification of one error. So that's an important reminder. And over here, you'd probably recognize these as 3 different distribution plots: a log distribution, a normal distribution, and a uniform distribution, which we'll also talk about. Quantifying uncertainty. So the example here is we have 2 rulers. One ruler has a tick mark for every unit, and meanwhile you have a tool that's more precise, and you can have measurements of a more precise level with this type of tool. So the first step in uncertainty analysis is really identification of the potential sources of uncertainty. Again, inputs, assumptions, boundary conditions in a model or process. Next, we look at the probability distribution. So understanding the distribution of uncertainty is really the second and very important step, often overlooked, frankly. The third step is uncertainty propagation and or management through a variety of methods: Monte Carlo simulation, bootstrapping, and ensemble methods. Louis going to talk more about those in a few minutes. On the right here is an example of a Monte Carlo simulation where if you only use 10 points to do this statistical analysis and draw a circle, you don't really have many points to actually define the circle. The more points that you have, the more your ability to draw the blue circle, either through the red dots or the blue dots, which then depends on your value of pi. And lastly, sensitivity analyses. Sensitivity analyses are something that we talk about a lot, you've probably heard, and let's examine that a little bit more. So what is a sensitivity analysis? Well, it's an important and integral part of uncertainty analysis, but it's not the same as uncertainty. That's important to remind ourselves. Sometimes these terms get used and there's almost an assumption that sensitivity analysis is the same as uncertainty, but it's not. A sensitivity analysis is an assessment of how sensitive a model is to changes in inputs and or data. It helps determine the relationship of uncertainty in the model outputs and inputs. And through using sensitivity analyses, we can gauge what the root causes of uncertainty in the model are. So this is from ASTM that came out early when groundwater modeling was first developed. So I'll walk through this diagram here because it really categorizes 4 types of sensitivities. So on the column on the right here, we have a sensitive parameter that's sensitive to the calibration of inversion model, an inverse model. And then we have another column which is insensitive to that calibration. So a parameter can either be sensitive or insensitive to a model's calibration. And then along the rows here, we have a model results that do not change and model results that change. This is the difference between, how much your model actually, your prediction is actually different. If you ran the model with different parameters, how much would it change? So we start out here. Type 1 is a model result does not change for an insensitive parameter. So your parameter is insensitive and your model doesn't change. It's not really that important on your type 1. Type 2 model results do not change for a sensitive parameter. So again, if the model results aren't changing, that's not necessarily impactful to your prediction, but it's important to know what your sensitive parameters are, particularly when your sensitive parameters do affect the model results itself, which is model results here in type 3. Model results change for a sensitive parameter. Now, we often talked about our sensitive parameters and how we want to maybe learn more about those, but it's important to remind ourselves that if the parameter is sensitive and the model results change, that means the inversion itself can be a fairly good approximation tool for estimating the parameter value itself. Lastly is a type 4, and here we have a model results change for an insensitive parameter. So think about that for a second. You have an insensitive parameter, meaning you can change it as much as you want in the model inversion, but the calibration doesn't get any better or worse, but you actually get a different prediction. So that type of sensitivity is one that is most concerning to groundwater modelers because we use the inversion to help refine our parameter estimates. But if our parameter is insensitive to the calibration, then the inversion is not making any impact in the accuracy of that model parameter estimation. And you're getting a different result if you have an inaccurate measurement. And from there, I will pass it over to Louis to talk about some tools for quantifying uncertainty.
Thanks, Jim. So I'm going to be going over some of the ways in which we quantify uncertainty in our day-to-day here at Parsons, especially as related to groundwater modeling and geostatistical analysis. I'm going to be focusing on some publicly available and open source methods, as well as we'll jump into some closed source methodology as well, which I'll get into on the next slide on publicly available methods. So when it comes to groundwater modeling, the most widely used program is the parameter estimation tool, also known as PEST. It's free to use, and it's going to determine the uncertainty in your model outputs so that you can minimize the error in your estimates of what you're inputting into the model. In addition to PEST, which PEST is written and compiled in Fortran, much like another program I'll talk about later. But in addition to PEST, you can also use Python, or you could use something like R if you wanted to, or whatever programming language you're most familiar with. But Python has a lot of suites available to determine what your uncertainty is, and you could either use a pre-made package or you could write it from scratch. A package that I've used a few times here at Parsons is called UncertainPy, and it's a toolbox that you're going to be able to use to quantify uncertainty and conduct your sensitivity analysis. And it was made with a neuroscience research background kind of in mind for what it would be used for. What I want to point out, though, about pest and uncertain pi is that both of those are effectively treating your model as a black box. That means that you can use any type of model in them. You might have to tweak some things to actually make it run your model. But in summary, it can run any model. It's just they're highly optimized pests for groundwater modeling, uncertain pi for neuro research modeling. But you could also write up some of your own uncertainty propagation scripts in Python that I'll be getting into on the next slide that you can use from statistical toolboxes that are well known and documented. One of which is Monte Carlo analysis. I use that a lot if I were to write something up from scratch. That will allow you to constrain a probability distribution so you can see your possible outcomes by implementing pseudo-random numbers into your simulation. And this is a very basic explanation of it. It's a bit more complex than what I'm letting on. Another method is bootstrapping, where you're going to take a sample of your data and you're going to resample it randomly so that you can then simulate other conditions later on, whether it be forecasting or if you just want to see how a certain function might work if the data was a bit different. Another way in which you can propagate uncertainty is to use a smoother. That is going to look at your data and it's going to smooth it out by basically extracting the useful trends in your data. A very popular smoother is fast Fourier transformation that will take your data, put it into the frequency domain so that you can extract useful data from it that way that you might not be able to see kind of with the naked eye otherwise. Another thing that you can do if you wanted to propagate uncertainty is to combine all these different methods. This is what would be known as an ensemble method. And when you have an ensemble method, you're going to basically, much like when you hear about an ensemble cast or an ensemble group of whatever it might be, you're taking multiple things and you're putting them together. So an ensemble method would be if you were to take more than just one propagation method, and I get into some ensemble methods on the next slide. So typically in groundwater modeling, when we use an ensemble of things, we'll use an ensemble of smoothers. And what that is going to do is an ensemble smoother is going to take two or more smoothers to produce a more accurate prediction of your inputs. These have been used historically for the reservoir history matching problem, which is from the field of petroleum research. What that basically means, the history matching problem, it's this idea that if you can take prior constrained data and observations and put it into a model and accurately model those prior conditions, if it's able to do that, you're able to effectively field verify and you're able to validate your model, which then means that you can then also forecast things for the future. When you use an ensemble smoother in this way, it is going to give you a single global update, which is going to use all your data simultaneously, but this leads to a trap that is on a graphic that I'm about to pull up, which is going to basically mean that you can fall into a local minima trap when what you're looking for is the global minima. So when you fall into these local minima traps with an ensemble smoother, there's a chance that you could fall into one of those red dots that you see, even though they're very far away from the actual global minima, and your ensemble smoother may not have checks put in place to then say that it can keep going. It might stop there and say, this is what your answer is, when in reality, it's not the most accurate answer. And the way that we get around that is to make the ensemble smoother iterate over all these local minima, which I get into on the next slide. So the iterative ensemble smoother is basically going to be able to take all those local minima that you're seeing, and it's going to be able to iterate through each of them so that it can actually locate the global minima. It's going to use Gauss-Newton iterations to search for the ensemble of the minima of what is called the cost function. And what it's going to do is when it gets to these local minimums, it's going to then give you a suite of what the possible inputs are based off of those local minimums. So it's going to take your model and it's going to find a local minima and it's going to basically then save it and say, we're going to put this to the side for now, but we're going to keep looking and see if we can find a better result. When it gets this suite of possible inputs, it's then going to push all those through the model and give you a batch of results so that you can calculate uncertainty. This has been used for a very long time in the atmospheric sciences and in meteorologic sciences. We typically see it with something like hurricane tracking, where it's going to take all sorts of different, very plausible inputs to the model, and it's going to run them all through and effectively give you these guardrails that are going to show you what the potential outcome could be when it comes to hurricane tracking. Let's say if it was trying to determine, the probability of certain wind speeds, it's going to run the model a lot, and it's then going to give you all these different outputs of what is plausible so that you can effectively constrain roughly what the result is, and it's going to have a high level of accuracy when you do that. And I'm going to get into on the next slide how this kind of applies to groundwater modeling more directly. So when we're groundwater modeling here at Parsons, we use it for a variety of functions and purposes. Some of those might be to just forecast, for instance, what groundwater levels are going to be on a site. We might use it for remedial decision making, fate and transport modeling. There's a lot of different features in which we might want to produce a groundwater model. And groundwater models are inherently deterministic. And what that means is that our groundwater models that we use are going to have just one single answer. When you have a deterministic model, that basically means that if you have identical inputs between model runs, it will give you the same exact result every single time because there's no randomness that are put into it. These models typically are going to be based on differential equations that will describe your system, but in order to actually ascertain an adequate result, you're going to need a lot of data, which is oftentimes not feasible to collect. These outputs of a deterministic model, they can be either continuous through time or they can be discrete. And the takeaway of what a deterministic model does is that it's basically, if you were to try to ask it what the answer to something is, it would tell you based off of your question, this is the one and only answer to it. In order to improve how we're able to run these models, we need to add a different element in, which I get into, which is probabilistic models. A probabilistic model, also known as stochastic, I apologize if I use those terms interchangeably because they, for our intents and purposes, pretty much are. Stochastic models, those will implement randomness and noise so that you can obtain numerous results. They're going to take into consideration the sample size of your data, the uncertainty in your data, and your parameters, as well as they're going to, by introducing noise and randomness, somewhat account for what I'm going to call intangibles. Those are going to be inputs that you can't quite quantify, but still do exist in your system. Just like a deterministic model, these can be continuous or discrete outputs. And a stochastic model, the best way I could put it is that it would be like if you were to ask it a question, it would tell you, based off of your question, this is a suite of probable answers. So it's going to give you a lot of different answers. And on the next slide, I get into our groundwater modeling is typically done through a program uh, or a compiled package, I should say, called ModFlow. ModFlow has been compiled in Fortran, and it's going to be an inherently deterministic model. So if you were to run a ModFlow simulation and you were to run it once and then run it a second time and you don't change a single thing, it will always give you the exact same result. So in order to improve our groundwater model calibration, we need to implement elements of stochasticity into it because otherwise we would need to have very intensive data collection and implementation, which can not only be very time consuming and costly, but in some instances, it might just not even be an option to begin with. And I'm going to get into following this, some of the advances in groundwater modeling that we can take on, which I'm going to primarily go through the development and advancement of PEST. So remember, PEST is that parameter estimation tool that I was discussing before. PEST is effectively going to take your model parameters as inputs, and it's then going to solve the model using that range of inputs that you give it, and it's going to try to reduce uncertainty along the way with your inputs by using a gradient descent of the cost function, which is a kind of cornerstone of machine learning algorithms, is to use the gradient descent of the cost function as you minimize error. PEST came out in about 1994, and it was all looking good, but then there was a want and need as these models became more complex and as more data became available. There was a want and need to make it run faster. So the way to do that is that along the way, PEST HP came out. The HP stands for highly parallelized environment. It's going to run incredibly similar to PEST. There are some changes that have been made here and there that are a bit insignificant to the actual mathematics behind PEST. But what it will effectively allow you to do is it'll let you run your model off of various devices all at the same time, or say if you were using one device, it'll let you use more of your computing power to run the model so it can calibrate faster. The newest iteration of PEST is PEST++. You'll see it as PEST PP. Sometimes it is PEST ++ sign. PEST++ uses an iterative ensemble smoother, and it's going to use, in this case, a Kalman smoother that is going to be optimized for posterior uncertainty analysis when there is nonlinearity between your model parameters, which are your inputs, and your model outputs. And it's going to give you a parameter field based off of the uncertainty of your prior distribution in your model. So there's different ways in which we can use PEST. This next slide, I'm not going to spend too much time on, but I want to have you as the audience take away that there's more than one way to actually use these programs. You can use these programs in user interfaces or non-user interfaces. And the main takeaway of one versus the other is kind of what you're trying to actually do and what you're trying to accomplish, which I actually describe a bit better with the graphic that's on the following slide that is going to explain your level of effort. But first, I want to explain with your different modeling vehicles. It's something that my advisor from grad school had kind of put together that I really took to, because I think it resonates with me with trying to explain these different ways to make your models. Effectively, if you had wanted to make a model in something like a spreadsheet, that would be like, if in terms of vehicles, if you were to walk to your destination, you'll be able to get to your destination, but it's going to take you a very long time. If we were to want to do something that was a bit better than walking to our destination, you might do something like take a bus. In our case, taking the bus is similar to a closed source commercial program that's going to have a user interface. User interfaces, they're going to be nice for ease of access, because you're going to be able to have drop-down menus and arrows and buttons and things like that you're going to input all your data into, and it's going to kind of guide you through. But much like taking a bus, it's going to be not the fastest option, and it's going to be a very rigid path that doesn't let you really customize the way in which you get to your destination. If you wanted to have an option that was even better than taking something like a bus, that would be like in today's standards, if you had something like a car, or primarily I'm going to refer to it as a Tesla. In today's standards for groundwater modeling, that would be like if you were to use something like FlowPy, which is a Python compiler for ModFlow. It's going to get you to where you want to go. It's pretty customizable in terms of relative to the other methods, and it's becoming the new standard of non-user interface modeling. But if you wanted to go to an option that was even better than all three, you could do something like use Fortran. Fortran, my advisor and I both really like to think of it as kind of like the red Ferrari from Magnum PI. Fortran is pretty classic in terms of data analysis and analytics when it comes to these sort of sciences, but it is becoming a bit older and a bit dated. And if we go to the next slide, we'll be able to see kind of just a basic comparison of these different methods in which you can run or compile these models. If you were doing something that was fairly basic, you can see on the graphic below, if you were doing something like a Darcy column or just like a basic 2D model, if you were to use something like FlowPy or Fortran, you might be picking up a lot more work than what is actually necessary. And there are instances in which something like a spreadsheet or an interface is actually the option that might be best, depending on what your projects are. But as your models become much more complex, you're going to see that the level of effort that you're going to be putting in to use those more basic methods of creating a model are actually going to kind of stall out, and you're not going to be able to get as much done. And that is where, when you get more complex, your effort is actually better focused on those more complex methods of putting the model together, something like FlowPy or Fortran. And with that, I think I'm going to be turning it back to Jim.
All right, thanks, Louis. So in this next component of the presentation, we're going to talk about a specific toolkit that we've been developing and are continuing to develop in our research and development group here at Parsons. And it's specifically related to PFAS modeling. So in order to get into it, I want to try and spend a little bit of time talking about the math behind our groundwater models. Not necessarily the tools in this case, but the actual math, because it relates to how we think about PFAS in comparison to how we've thought about groundwater modeling for what is essentially decades. So over here, this is the groundwater fate and transport, advection, dispersion, retardation, degradation equation. So let's think about this for a little bit. It's not that complicated. I'll explain the parameters so that you don't have to read through what all of this means. So over here we have the three components of dispersion. So longitudinal, lateral, and vertical dispersion. We have our velocity term here. We have our decay function here, and then we have retardation. So in the past, we might think about groundwater velocity a lot, particularly what is our hydraulic conductivity. We know hydraulic conductivity can be fairly influential in groundwater fate and transport, particularly for volatile organic compounds, for example, or dioxane, PCE, PCE, those kind of compounds. We've known and recognized the importance of groundwater velocity as an important component to this equation for a long time. What have we thought about dispersion? Dispersion, we usually don't have a lot of information for, so we do our best estimate based on the plume length, and we try to manage that through the inversion of calibration. It's a bit of a tricky parameter, but it oftentimes doesn't fall into that category of will change the model result much based on general priorities for our fate and transport modeling. It definitely affects the plume more importantly or more influentially out in time and distance, but we don't really manage the dispersion function much differently between PFAS and other compounds. We talked about velocity already because that's an important one. Now let's think about PFAS and decay. Well, PFOA, PFOS, everybody's calling the forever compound. So that really goes away. That makes it different than most of our other fate and transport processes where our plume is actually going slower because of decay. What have we thought in the past about retardation? Well, retardation is what slows the plume down essentially from from, most importantly, sorption. And sorption is a function of the octanol water coefficient for an organic compound and the fraction of organic compound in the soil. So how much does the compound sorb to soil, and how much of that soil is sorbative, if you will. I've put porosity over here because that's also a very important parameter when we talk about average linear velocity. The average linear velocity equation, if you all remember, it has porosity in the denominator. So the lower the porosity, the higher the average linear velocity. In this toolkit that I'm talking about now, I'll briefly mention porosity. We did a similar parameterization for porosity as I'm going to show for sorption, but just recognize that although I don't get into all the details here, it was part of the uncertainty approach to this PFAS toolkit that we've developed. I also included the average linear velocity with retardation down here because it's in the denominator of the velocity of the compound. And what have we done in the past? I've mentioned what we did in the past, thinking about velocity and hydraulic conductivity. Hydraulic conductivity is hard to measure, ranges by an order of magnitude. Well, usually in the past for retardation, like I mentioned, we look up the octanol water coefficient. We make an assumption, usually a conservative assumption about what the fraction of organic compound is. And then we develop essentially a conservative model that may, if nothing else, underestimate retardation to give us some sort of inherent safety factor. Now, if we move through this toolkit itself, first let's talk about how the toolkit handles flow, and then we'll talk about how it handles particularly the other parameters. So what we've developed is a test model, a synthetic model, and a process for managing and estimating uncertainty in phosphate and transport. It started with a mod flow model. This was a pilot point model. I actually simplified it for the hydraulic conductivity field in order to improve some efficiencies. The pilot point method is more of a way to have a probabilistic model, as Louis had mentioned earlier, but in some cases you get a similar result with a non-pilot point model. So with the simplified hydraulic conductivity field, we established a suite of ensemble outputs using PEST++, with a very simplified approach in order to build a suite of results for the uncertainty prediction set. And what this amounted to was 9 iterations across an ensemble of 40, which is then 10,600 runs, and 8 final iterations were retained. And here you can see the PEST++ runs, and the beauty of this slide is how the phi for each of these runs reduces down to almost the same level of accuracy for the model. And here what this is showing is, here's the prior distribution. This is essentially the residuals, and this is the prior distribution, as Louis had mentioned. And then you can see how there's a left shift for each of the model runs themselves, which indicates an increase in accuracy of the model because the log residuals are decreasing in this direction. So that's the flow component. Now let's talk about the sorption component of PFOA and PFOS in particular, because what I mentioned before with our typical volatile organic compounds and our numeric modeling of those, we think about retardation and how sorption is played into that. And like I said, there's usually a relatively small number that we can do a simple lookup and figure out, what the range of estimates would be and vary from there. With PFOA and PFOS, we can have between 1.5 and 4 orders of magnitude variability in your absorption coefficient here. And this is based on our PFAS team of experts, their experiences, as well as sites that we're currently analyzing. We're going out and developing site-specific absorption coefficients. And it's important to note here that, for PFOA, PFOS, and other compounds, absorption is a nonlinear isotherm. And what that means is, depending on how high your concentrations are in the aqueous phase, you could have variability in your KD. And again, why is this important? Going back to the retardation factor here, you can notice how the absorption coefficient is directly related to it. So if you have an unknown parameter of your absorption coefficient, and it could be 10 or 1,000, in this equation you can directly see how influential the absorption coefficient is related to retardation. And again, retardation, going back to the fate and transport equation, is directly related to that transport. And why is PFAS so complicated? Well, not only does it absorb through classic hydrophobic methods, which you can see over here, there's also electrostatic methods that come into play, and fluorophilic absorption concepts where PFAS is essentially sorbing to other fluoride. So what did we do to build this model out? This is essentially a set of steps that describe how this uncertainty model was built. We started with querying the literature and site samples for a bracketed absorption set of parameters in order to derive some statistically based set of parameters for our suite of results. We developed a set of normalized random distributed flow cells. So the first thing we did was distributed our KD through our flow field through a random set of flow cells, and then developed a normalized random values from a known range of KDs, gradient, and porosity values. So first we developed the set of flow cells, and then for every flow cell, based on the distribution in a bracketed range for absorption, gradient, and porosity, we developed a suite of results from each of those statistically based distributions and assigned a value to each one of the flow cells in order to estimate what the PFAS transport would be from essentially, the bottom of this set of flow cells to the top. From there, we developed a suite of 28 Phaeton transport scenarios in order to provide a basis for analysis in terms of how our PFAS transport might range. And to answer the question about ranges in concentration for the source area, we developed two groups of 28 model runs with varying concentrations from 1,000 nanograms per liter down to 100 nanograms per liter. So next slide here. This is just the results from the high range. Going back, that's the 1,000 nanograms per liter here. And as you can see on the left-hand side, this is our PFOA concentration in nanograms per liter, and this is our distance from the source area in feet. What's sort of remarkable and highlights the importance of our absorption coefficient in particular is the wide range of plume distances that we have. Here are a set of runs from our 28 runs, and this is at 40 years. So asking the question, if I had a PFOA spill that made it to groundwater 40 years ago, how far would the plume have traveled under this set of parameters? And the results, like I said, have a significant variability, somewhere between 2,000 and greater than 6,000 feet. So given that, it really begs the question, and thinking back to the type 1 through 4 sensitivity categories, as I showed earlier, what's important here is we have a set of parameters that have significant change in the model output. So that's the rows on that diagram I was showing before, where the model change is affected by the change in parameters. So PFOA, PFOS, their sorption in particular, and I'll sort of demonstrate this conclusion on the next slide, but sorption in particular becomes important in terms of that sensitivity and model change, well, particularly the model change. So in this slide here, I'll explain the graph and then we can get into the results a little bit. So on the y-axis, primary y-axis, we have the sorption coefficient, and you can see it's got a very significant range, up to greater than 2,000. And we have an average linear velocity on the secondary axis. And take note of this average linear velocity range. It's very small, only ranging from 1.1 to 1.6. Might end up with more variability in a typical site, but these two y-axes are plotted so that essentially as a graphical representation, both the KD results and the average linear velocity results are overtopping one another. What is this graph telling us? Well, it's telling us a couple of things. The average linear velocities, which are these orange dots, there's no relationship to our plume distance and these ranges of average linear velocities. You can also notice that there's essentially no correlation. What we notice with KD is there's a significant relationship, and I'll go from right to left here, a significant increase in distance as related to the sorption coefficient. So as your sorption coefficient is going down, your distance is increasing. So again, as your sorption coefficient is going down, your distance is increasing. And that's somewhat expected. What can be unexpected is the large range in sorption that you might observe at a site. So effective and efficient uncertainty analysis and prediction sensitivities can be developed through rigid statistical processes and commonly available tools. So it's something that we've derived with this set of tools here, is looking for fast, efficient, simple models, but using those models to derive a suite of results and complete predictive analysis in order to quantify the uncertainty of fate and transport, particularly of PFAS. In this case, the plume ranged from 2,000 to 6,000 feet in a distance of 40 years. Again, representing a large range in distance, and really bringing in the final point here that PFAS is highly sensitive to sorption, and at most of our sites where we're thinking about this, we're talking more and more about site-specific sorption parameters to really bracket, create a tighter bracket for the sorption coefficient and try and bring in this range of distances. And in conclusion, uncertainty analysis and sensitivity analysis are an important part of mathematical modeling. If you're a manager, you might not, know all the intricacies of the mathematics behind it, but it's important to ask certain questions and important enough to be informed that your modeling team is taking the right approaches and thinking about uncertainty analysis. There are multiple tools, particularly the PEST suite, which has been improved over time, as Louis had brought up in his presentation. And in our example here, our Parsons PFAS modeling developments are a mechanism to mathematically evaluate uncertainty in a computationally efficient manner. So taking a lot of those concepts from very complicated tools that take lots of resources and time to develop and use, but simplifying those and bringing those down to a more practical level for use on a multitude of sites, and kind of developing it with the concept of principle of parsimony, building your complexity up as needed. And since we're talking about drawing circles, and we have so many circles in this presentation, one of our colleagues made note that it was a reminder of this Kenneth Nolan art askew back from 1958. I'm going to close with acknowledgements. We're really nothing without our team and the people that support us and help us along the way. So I'd like to acknowledge Kyla Wyatt, Hannah Annunziata, Melanie Beck, and Jeremy Stock, all which played parts in the development of our tools, and particularly this PFAS tool at some point in time. And with that, we're going to open it up for questions.
Yeah, thank you, Jim and Louis. That was a really great presentation. I know modeling is used in so many projects, and this really helped explain some of the really important concepts to keep in mind for modeling. If there's any questions, you can either raise your hand and ask your question live, or you can enter it into the chat and we'll read it off.
Hey, Ryan, see you have your hand raised.
Hey, thanks. Great presentation, Jim and Louis. I appreciate that. This issue of correlating the specific PFAS physical chemical properties to, what's actually observed in the fate and transfer behavior is quite important for, site characterization. So I appreciate you noting that here. But my question is related to really the differences in statistical methods. I'm familiar with using density functional theory with Monte Carlo to evaluate molecular dynamics, but I'm not so familiar with, bootstrapping. So what's the main difference between, Monte Carlo and bootstrapping?
I'm going to pass it over to Louis to take that one.
Sure. So when we think of bootstrapping, that's more going to be along the lines of when you're going to take a data set you already have and you're going to resample it and use it typically more for forecasting possible conditions, as where Monte Carlo, much like the example with determining what pi is, Monte Carlo is going to be something we're going to test possible estimators of a theoretical environment. And I think it's interesting, just as like a side note, Monte Carlo analysis was named for the city of Monaco, where it's very well known for its gambling. And bootstrapping was named because of its ability to basically create something out of nothing, which is a lot like the one phrase that we hear often of, pull yourself up by your bootstraps, because it is quite physically impossible to do that. But when it comes to bootstrap analysis, it's kind of like you're taking a data set you already have and you're trying to just extract as much data from it as possible by resampling and running it again.
Yeah, that's a good way to summarize it, Louis. I think of it most predominantly as you had said, bootstrapping is really using the same data set essentially, and sampling from that same data set, where Monte Carlo, which is something that we use a little bit more of in numeric modeling, is provides the ability to, result in multiple outcomes.
Excellent. Thank you.
We have a few questions that have come in through the chat from Julian Chambert. What methods exist for sensitivity analysis, and what is most utilized in groundwater modeling?
As far as sensitivity analysis, there's a few different ways in which you can do it. One is that you could run your model with individual inputs where you incrementally change it and do a visual analysis of, say, a scatter plot of your inputs and your model outputs and their uncertainties. What we use in groundwater modeling, it's quite literally called one at a time sensitivity analysis, where it's fairly similar. You're going to calculate your model outputs while, again, you're incrementally changing only one input and keeping everything else exactly the same. And you're then going to see what your uncertainties are looking like when you do that. Other methods I'll just run through is, you could take partial derivatives of the output with respect to your input to derive an uncertainty. You could perform regression analysis, or like I had mentioned, fast Fourier transformation. You can do a Fourier transform where you basically extract useful data such as the frequency to determine what your sensitivity is.
Okay, next question is from Taylor Schweigel for Louis. Is there a difference in computing time between PEST and PEST++ IES, and if so, why?
There typically is going to be a difference in computational time. PEST++ IES is going to, for the most part, it's going to be faster. It really depends on how you pose the problem that you feed into it. But the best way that I can describe it is PEST is going to use that gradient descent, kind of machine learning type of algorithm to find one single global update for your model, as where PEST++ IES, it will calculate your sensitivity and correlations between the inputs and outputs as you go. And in doing so, it's basically going to approximate like these little results that are all close to being correct. And it's going to use that to just try to reorient the direction that it wants to move in. And I think that, the best way I can kind of put it into like simple terms is that if you were trying to just determine what in Buffalo, there's a lot of like pizza places here, and you wanted to know what the best place was. If you were to use a method such as how PEST would do it, that would be like if you were to go to each place individually in isolation and try everything they had and then try to make a decision at the end of what was the best, as opposed to PEST++, the way that would operate. It would be like if you use prior data such as reviews of pizza places, as well as just knowing what places already are probably going to be good, going to each of them at the same time, taking a little bit of what they have, and then trying to make a decision based off of that together when you have everything in sequential order.
Thanks, Louis. The next question is from Daily Valent. How do you manage the level of effort for a particular problem, given the wide variety of modeling approaches, tools, etc.?
Yeah, level of effort. So in thinking about that question, every site is unique, and every site has very specific objectives. And for us, myself especially, the first thing in terms of level of effort is really to consider what the site objectives are, what the data set is that you have, what the overall project perspective is, and really tailor every model. Essentially gets tailored to the site specifics, and even sometimes the client objectives. What are we trying to do at this site? What's the current conceptual model? What's the risk profile? What is the model actually going to be used for? Every modeling project starts with what is the objective. So really that objective gives us a guide, because it's a very salient point, Bailey, in that there's a lot of different ways to model and a lot of different tools. And there are significant differences between simple models and very highly complex models in terms of level of effort and what essentially comes down to dollars and cost. So we typically follow the principle of parsimony and start simple and build complexity as needed, because we might opt out of the modeling process earlier by following that philosophy. And if you can do that, then you can answer the question. You can essentially complete the objective for the project, but do it at a minimal cost.
Thanks, Jim. It looks like we got one more question that we'll wrap up with from Sarah Fisher. In the assumption PFAS is conservative and does not degrade, does Parsons models typically consider total PFAS? It's my understanding that PFAS precursors can transform and change the distribution of individual compound pools.
Yeah, that's a great point, and that's why we put it in the assumptions, being completely transparent. Right now, within, I would dare say, all mathematical models for PFAS, the hardest parameter to really get details on is the precursor issue and creation of other PFAS. So there's PFAS that we're not measuring, there's precursors that may be transforming, and there's not a great modeling method for it. I think as the industry evolves, we'll continue to use uncertainty tools and continue to use our mathematical processes to better understand and quantify that. But Sarah, it's a great point, because this type of approach is really specific to something that there might be a known source or a better understanding that there are not a lot of precursors. So at some sites you might have PFOA, for example, that was a product, it was spilled, and we're now trying to model it, and there are limited precursors.
Okay, I think we'll wrap it up there. We're at 2 after 12:30. If there's anyone else has a question that you didn't get asked today, please feel free to reach out to our presenters directly. Their contact information is up here. A link to the form for PH credits has been posted a couple times in the chat, as well as the questions. If you had any issues downloading that form, please reach out to us and we'll help you out with that. And the recording of the webinar, if you missed anything, will be posted on our YouTube channel in the next few days. If you can go to our next slide, please. Our next webinar will be in January 2025, and further details will be posted in the next month or so about that webinar. Thank you to everyone who joined us for today's webinar, and we hope to see you again in January.